Log on, tune in, find out. Another good idea from Cambridge.
And Sebastian Reich, whom you will all know and who is here. My talk is concerned with data assimilation, and just a very brief, I assume you all know this, overview what I'm going to do. Data assimilation tries to combine information, noisy information we get from a forecast and from observations and produce an analysis. And the analysis is obtained by incorporating forecasts and observations and their associated errors. And then this analysis is taken as a new initial condition here for our next forecast. And then again, we get here an error covariance and a new estimate, and we combine it with another observation that comes in, produce a new analysis, and so forth. There are lots of ways how to attack this problem. And what we are interested in is, well, first an analysis, so that's actually the state or estimate of our state, and also the error covariance associated with the state. So how much can we actually trust our analysis? And I've written down a few here. So one is optimal interpolation, then there's 3D var, 4D var, and there are Kalman filters. And we're going to work here with ensemble Kalman filters that have been introduced in 1996 by Evanson. And they have the following properties. They are optimal filters, provided that the process is Gaussian. That's in common with all Kalman filters. And the nice thing about them, though, that distinguishes ensemble Kalman filters is that the error covariance is propagated with, or you get the error covariance from the full, propagating the full dynamics, and not by any linearization. So our setting here is, we have a dynamical system, z dot is f of z, so z is in some Rn. We have a perfect model, there's no model error here. And then we have observations, we call them z-ops, they're taken at equal distances, spaced by delta t-ops, that's our assimilation window. So every delta t-ops, we make an observation and an analysis. We have an observation operator that goes from our full state space Rn to this much smaller observational state space with dimension p. And we write observations as this observation operator acting on our truth, and then we say, okay, there's some error here, some Gaussian error R-ops that has a specified error covariance, capital R-ops. This is all standard now, and this is Evanson's idea. He says, okay, we're going to consider an ensemble of k members, and we propagate all these z1s to zk's in time by the full nonlinear dynamics, and they're initialized by some zb, our background state. And the ensemble we can split then into a mean, we call this z bar, and into a deviation matrix z prime. And then we can formulate defining a best estimate, giving noisy forecast and noisy observations as minimizing this cost function f of z, s of z. And so what you do in the ensemble Kalman filter here, I'm going to tell you what transform means in a minute. We propagate our background with the full dynamics, and we get a ZF for each ensemble, for each of these k states. Then we estimate, and this is the key issue of the ensemble method, then we estimate the error covariance trivially by just doing the z prime transposed of the deviation matrices. Okay, so we get that one for free. Usually PF is rank efficient because the number of the ensembles k is usually much smaller than your state space. Then we have to do the analysis, and the analysis is given by the standard Kalman corrections, the Kalman formula that we just get by minimizing this cost function. And we get an analysis error covariance matrix PA. Get that for free, so we know how much we can trust our analysis. And then we have to update our ensemble. So now we've propagated we've done the analysis. Now we have to look for, so we know what our PA is, but we don't know what our ensemble has to be, how we have to choose our ensemble. And what we require is that the new ensemble that we take then as an initial condition for our next cycle is consistent with the analysis covariance that we calculated. So that's this condition here. And so we have to solve this. And there's several methods, or the methods I'm going to use is ensemble square root filters. And there's two main classes. And we're going to use this one here, where we write the deviations of the analysis here that we would like as the as this linear combination of our forecast deviations. And then we're done, because now we have a new, now we calculated the ZA prime, we know what ZA bar is, and then we have a new initial condition and we can continue. Okay? So this is standard ensemble Kalman fitting. And here just an illustration how that works. So let's say this is our truth. Then we take some observations. They're noisy. Then we create an initial ensemble with some specified covariance. Let that unpropagate with the full model. And at this time here, get all these forecasts. Then we can take the mean of this forecast. And now is okay, we have this information and this information. They both have a certain error covariance. So we create our analysis up here. And we also know now our PA. That means we can draw a new ensemble and do the same spiel again, doing getting our analysis mean, then getting the forecast mean. So then and then the green is our analysis. However, there are some problems with this standard procedure in our practical problems. And one big problem is that we do not have as many observations as we have variables as our state space. So that means there are large unobserved regions. And
I don't think the difference is as big as that if you allow for satellite data.
yes, I'm not considering satellite data here. I mean, they have different problems with bias. And
I think the difference is more, you've got 10 to the 3 as compared to 10 to the 8 haven't you, on that side. I thought the difference is more like a factor of 10 than a factor of 10 to the 5 in operational systems.
Okay, that you must be right. So I'll like to talk to you about that after. I've got this
It's still
from somewhere.
deficient, but it's not as deficient.
But here we see an illustration of this, maybe not the factor of 10 to the 5 here. Color coding is when these observational stations were introduced in time. And you see there's sort of large regions here. Australia in the center is one of them, and Africa up here in the north. This picture is not that great. This is sort of a regional thing. It's great when you give a talk in Australia, because then you know you've got Sydney somewhere here, you've got lots of observation stations and you've got nothing there. Cambridge is here, so they must obviously have a very bad forecast here. That's not, no, I mean, that's nonsense. But so this slide doesn't work that well in England, but because England's very well covered, as you've already seen here. Okay, so what's our setting here? So now we start with something new. This was all known. So we assume we have some proper observations with access to make observations. And then some other, and we call them observables. And there are some other variables, we call them pseudo-observables, which are not directly observable. We have no direct observations of these variables, but we have some knowledge, some statistical, let's call it climatic knowledge. So let's say we know the mean and the variance of the variable at these sites. And applications are these sparse observational networks. So we would know the mean at these other sites and the variance. If you can't make any observations, even with satellites, and this is if you want to forecast the mesosphere, there's this kind of sea of gravity waves, then that's not possible to measure them. So you could use something like this. Or if your system involves slow and fast processes and you have no direct access of the fast variables. And I'm going to give you examples, like this one is sort of in depth, and then this one is sort of ongoing work that I hope to get to at the end. And the main question is now, how can we use this statistical information that we have or that we assume on these unobserved variables to improve the overall forecast? the overall analysis. So the setting is as before, but now let's say we have our state space. We can decompose it to x and y, where x are the observables and y are the pseudo-observables, for which we only have some climatic information, but now direct information. And let's call this information mean small a target and the variance a target. Then analogous to the normal observations we have, we now introduce a pseudo-observation operator, small h, that goes from the full state space to a smaller space, the space of the pseudo-observables. And associated with the pseudo-observables, we have an error covariance Rw. Okay. And now the question is, how do we choose Rw? Okay, we have to set up again a minimization procedure that involves this Rw. How do we get it? How do we have to choose Rw? And the naive guess that you just say, oh, well, yes, this Rw is just the variance a target. It's not right. It's only right in a special case. So we're going to see that. So we do exactly what we had before. We introduce a cost function that we then want to minimize. So this bit here is our old friend from the forecast. This is our old friend from the observations that we encountered just before. And this is this new bit here where we just say, okay, this measures the difference between the pseudo-observation operator on Z and the difference with the specified climatic mean of our pseudo-observables. And this is the error covariance matrix Rw, which we need an expression for that one. We need to be able how to calculate it. This one is given. This one I have shown how to calculate it using ensemble methods. And this one now is that's our aim, to specify this one. And for people interested in weak constraints, this sort of resembles, at least formally, weak constraints in variational settings. So we now go through the same motion as before. We want to know the critical points of our cost function, and we again get these Kalman correction terms here. So this is the old one that measures the difference between the forecast and observations, where projected with capital H into observation space minus the actual observations taken. And this one here is a projection of to the pseudo-observables and the difference with the specified mean of the pseudo-observables. And again, we can calculate the error covariance of the analysis. And here's this Rw that we don't know how to choose. But we now make a constraint, so we say, we're going to use it, that the variance of the pseudo-observables, so by restricting to the pseudo-observables, I just have to use our projection of our projection here onto the pseudo-observable small h on our analysis covariance matrix. That should be our target. That's what we said. We said we have this climatic information. We know the error covariance of the pseudo-observables. So this is our condition. And then we can use that by, this is just for convenience, we introduce some kind of v-twiddle here, and we get that in the end, get an expression for our Rw, well actually for the inverse. And this is this kind of typical Kirchhoff type rule for error covariance, where we add up, or where we have sums of, well, bring this on the other side of covariance. You may already spot a problem here. There's a minus here, so potentially this can be negative. So that's not right. Error covariance can't be negative. But let's go first discuss our naive expectation that this Rw is just a target. That's only possible if this term here goes to 0. And that one only goes to 0 either if the Rops or the forecast error covariance go to infinity, are very, very large. And otherwise, that's not right. Okay. However, as I just said, that for small error covariance PF, this necessarily is not positive definite anymore. So what we do, practically what we do then, is we diagonalize this expression here, and then we pick out those eigenvalues or eigendirections that are associated with the positive eigenvalues, and we update those, and the other ones we just don't switch on our variance constraint. So, in summary, what we're going to do, we have a background, we propagate it, background ensemble, propagate it with the full dynamics, get a forecast, and we get a forecast error covariance. Then, by using the formula that we just derived, we get an estimate for our analysis mean, and we get an estimate for our analysis covariance. And we have this RW minus 1 that we just calculate. Then we do the same thing again as we did before. We have to find an ensemble for our next step that's consistent with our analysis that we calculated. And then we take this as a new initial condition and keep on going. To understand how this filter works, let's first look at a little toy system. Well, actually the other one is also a toy system, but at a toy system that we can study analytically. So we take a linear system, where here we have an so here we have two oscillators. So this is an R4. We have two oscillators with frequency omega x, omega y. We have a damping term here, and we have a noise term, and we couple them. And I've used here some sort of a skew product structure, where only one variable is coupled to the other one just evolves. That's not necessary. This is just for convenience. You get the same results if you don't have this skew product structure. So we can solve this using ETO. We know a solution of this equation. And now we can look what are climatic means and climatic variances of these. So we can calculate the mean and the variance here. Note here that we have some restrictions for this to be positive definite. We have some restrictions here, and the restriction is that the coupling lambda is the coupling, has to be sufficiently small, otherwise this thing is not an error covariance, it's not a covariance. So this system has climatic mean 0 and a well-defined climatic covariance matrix. Now we want to investigate two things with this system. First of all, when is the filter actually switched on? When is this RW minus 1 or the RW positive definite? But even if it switches on, it doesn't necessarily mean that we improve the analysis. So we also have to look at an improvement of the skill. So we do this in two steps. We first look at when is the filter switched on. If we have an ensemble here, you see when you have an ensemble, the covariance could be, can actually be larger. So if I have just one trajectory and for small, I followed for some small time, or if I have an ensemble of trajectories for small times, this one in the time, if I do a time average, will not have acquired the covariance necessarily of a small of an ensemble. So for small times, you have to be careful if you calculate error covariances in an ensemble or in a trajectory. In the long time limit, of course, if I calculate in the end the error covariance, it's the same as if I take it from an ensemble, but that's not true for short times. So you really have to go into the setting of ensemble. Then what we do is we restrict to small observation times, because otherwise we can't get any analytical expressions. And then we can say that the analysis error covariance is roughly the forecast variance at the next time, and then we can solve this equation here. And this is this formula here, where we also introduce a delta to inflate our. We want to have the possibility to study inflation. So inflation is done if you feel like your ensemble will not have enough spread, then you just multiply your error covariance, or you can multiply your error covariance with a constant scalar delta. And so delta equal to 1 is just, if you just let it down to the error covariance inflation, and delta larger than 1 is if you do this inflation. And you get a value out that's roughly here. These are simulations, how often the percentage of how often the thing switches on as a function of your observation window. And so you see for small observation windows it doesn't switch on, but then it starts switching on and we get the onset right. So I mean, this is just a little test, but let's discuss this formula a bit more. Inflation helps because this thing here has to be negative. That was our condition for our system to actually produce a proper error covariance for the actual toy model. So this time can be negative. Delta becomes very strong. That means we always have a switch on. Okay? So even for small observation times, the filter will be switched on. And that is sort of intuitive. Like if you ramp up your covariance, the constraining, of course, has more opportunity to be switched on. There's more instances when when this variance constraining filter will be switched on. Just a caveat here: for large coupling, or if gamma x is small, this can become very large. So we actually leave our regime of small delta t. We can calculate that the eigenvalues of w minus 1, how they vary with the observation time window, and that's positive. So that means at delta t equal to 0, that means what we've just seen, that we, for larger observation windows, we get more switch-ons. We would not expect, if delta t goes to infinity and r ops goes to infinity, we would think, this is this argument here, our system will have acquired the climatic mean, so PF should go to sigma clim, and we would not expect this thing to be switched on, because we got the right covariance. But that's not true, and this is a finite size effect. So actually what we observe is that the filter is always switched on for large observation windows. So the next question is, when do we actually get a skill improvement? So now we know when the thing switches on, but is that helpful? And in order to do that, we look at an RMS. Well, actually the R is missing here, but an error here that we define as an expectation value over time and over realizations of our Brownian motion of our driving, our stochastic driving dw, of our analysis minus what we actually know about the truths, and we can look at this norm either for the whole space, just for the observations, or just for the pseudo observations. That's this G here. And then after some tedious algebra, you come up with these expressions here that are not very insightful, probably, for you know. And you can look at evaluating those numerically. And so what I've plotted here is this skill here of the error if we use the ETKF, the normal ensemble transform Kalman filter, and the error if we use our VCKF, our variance constraining Kalman filter. So if that one is larger than 1, we actually have a skill improvement compared with the traditional ensemble Kalman filter. So these are theoretical estimates, and these are our numerical data if we actually perform the Kalman filter as a function of gamma y. Gamma y is the decay rate of your fast variable. And this is without variance inflation, and this is with variance inflation. So this is, 1.01, and this is here 1.014, so there's an increase. Of course, you're going to say, well, for 1%, why bother? This is just for the toy model. I'm going to show you an example where you get like 10% skill improvement. So what do we learn from this analytics here? One interesting one is we got skill improvement if we say that gamma y goes to infinity. So gamma y is the decay rate of the fast process. Of the unobserved variables, Or gamma x goes to 0, that means that the decay towards equilibrium of your observables is very slow. So that suggests that it is kind of a timescale separation between the observed and the unobserved variables. So if the unobserved variables acquire your climatic mean quickly, then it makes sense to use this variance constraint, because you actually you force the system to have the variance that it actually has. Because if it decays quickly, then it will be close to the climatic mean after a short period already. So that means for this regional forecast where we have unobserved stations, this suggests that, we didn't find anything there, but this is more like a timescale issue here, that we expect this filter to work well in a timescale separated system. We also find that the slope of, or that S increases with increasing observational error. That also can be understood, but if the observational error is 0, then your filter will trust your observations, and that means, because we have a perfect model, that there is one Wiener process that actually will track the observations with the correct gammas and sigmas, the correct diffusions. However, if you put some error on top of it, then this process, the Wiener process tracking it, will have a larger diffusion if you would model it. And larger diffusion you can then interpret as a smaller decay rate. So we're back in this one here. We have a slowdown of the relaxation time of the observed variables. So this can be linked to this effect here. And what we discussed already, that the skill improves if we switch on inflation delta. So as I said, I mean, for 1% for these small skill improvements, that would not be very satisfying. So let's look at a different model here, another toy model, the Lorentz 96 model that I love very much. So you got variables Zi, and Lorentz proposed it as a toy model for mid-latitude weather, because he said, well, what do we want? We want some forcing, constant forcing F. We want some linear damping, and then we want some nonlinearity, but we want a nonlinearity that is energy conserving. So if I define an energy as just the sum of the Zi squares, then this term here, I mean, you can think of this term as a discretization of an advection term. Right? So this one is energy conserving. And then Lorentz said the following. So he wanted to make a connection with the mid-latitude. So he had a ring. These are all your variables Zi, they're equally spaced. And if this ring here is 30,000 kilometers, so this is one ring around the sphere here, then and we have 40, let's say 40 points, so 40 variables, then the distance between two of these observations, or two of these variables where the state spaces are, is roughly 750 kilometers. So it's of the order of the Rossby radius of deformation. And then he looked at the time scales of the system. So he looked at the e-folding time. And then Lorentz said that, well, if we have 40 variables and we choose f equal to 8, then one time unit is roughly 5 days, so that the 1 over Lyapunov exponent corresponds to the doubling time here. So our particular stand on this model is here. So these are all, let's say, our observation stations, 40 of them. So all these variables evolve now according to the Lorentz 96 model. But we said, okay, we only observe, let's say, every fifth component. But for all the other ones here, we said, okay, we know the mean and we know the error, covariance matrix. So let's specify the mean and our error covariance of the pseudo-observables. They're constant because there's a symmetry. So for each of these variables, they're the same because there's a symmetry in the system. And then down here, I plot in red is the truth, green are observations, and blue is the analysis. If we do normal ensemble Kalman filtering, so it's reasonably well. We track the truth. But here Z1 is one of the pseudo-observables, where we don't make observations, but we specify mean and error covariance. Red is the truth. So you see and blue the analysis. It's not doing so well. Now let's switch on this variance constraining. So again here, we can't see much with the bare eye. We're going to look at it in detail and quantify this. But here the solution is tracking much better the truth. So there is some skill improvement. I mean, just by the bare eye. But let's look at it now let's quantify this. So let's calculate the RMS errors. The RMS errors. Averages over D, the dimension of these vectors here, and time average. And here I've plotted this skill, so again, larger than 1 means skill improvement, as a function of our observation windows. And different curves correspond to how many unobserved components I have. Okay, so n ops equal to 3, I measure only every observation only for every third variable. And what we can see is, well, two things are obvious. Works better for small observation periods. And here for ns equal to 4, this is this green line, we get roughly the best skill improvement. But now let's look at how this skill is distributed over the observed and the unobserved, the pseudo-observables. So this is the skill here for observables and pseudo-observables, and this is the RMS error for both of them. Notice there is here an order of 1 difference in magnitude between the RMS errors of the observables and pseudo-observables, which you expect, but it suggests that the information doesn't travel much for the system from your observed stations to the unobserved stations. And we see again for small, we get skill improvements for both. For the observables, however, the dashed lines is the prediction from the ETKF, and of the same color the continuous lines of the variance constraining. So here you can see that for small, the dashed line is always above the continuous line, so the error we make with ETKF is always larger with the error we make with our variance constraining filter, and that's for all colors. But later on, ETKF can be better than VCKF, whereas for the pseudo observables we're always above. That's one observation. Well, let's skip this. Okay, so here we did the following experiment. We said we only observe at one site number 21. And then when we look at the RMS value, and we see it's huge everywhere where we don't observe, and it's relatively small where we do observe. We notice there's an asymmetry, and we also notice that information doesn't travel, or the skill improvement we make here doesn't really penetrate much into the unobserved size, only a little bit here. And the advection scale, or the advective time scale of the Lorentz system is much smaller than the delta T ops we're using here. So it can't really propagate that far information. And the asymmetry is because there's an asymmetry in the actual equations. So this shows you how still there's sort of a trade-off between, if you have too many, or if the space dimension of your pseudo observer is too large, if you have too many sites that are unobserved between two observed stations, then the error will be too large because you accumulate a lot of error on those many points then where you don't observe. Then we also looked at the phenomenon of blow-up. That sort of was first, I believe, studied by Ott in 2004. So the ETKF blows up in sort of for intermediate delta T op. So that means it just all the ensembles collapse. Your error covariance becomes singular, and your filter goes through the roof. VCKF seems to suppress this blow up. However, these solutions where we have even this kind of small percentage of blow-ups, this is 11% of ensembles will have experienced, or of simulation will have experienced a blow-up. Those ones are not tracking anymore, so you can't actually use them, right? I mean, it's only controlled, but it's not made better by using VCKF. But that's something I'd like to look into at a different time. So the question there that I would like to study here is what makes the filter blow up and how can you prevent it by choosing good initial ensembles. Okay, let's look at another system. Let's look at a slow-fast system. So we have a slow component x here. This is a double well potential. Well, I can hop. Well, I have two stable fixed points. If you ignore the blue one, stable fixed point at plus and minus 1, and you have an unstable one in the middle. So depending on the initial condition, you end up in one well or in another well. But then we disturb this, so this this system here, while y2, where y2 is a component of a fast, epsilon is small, of a fast Lorentz system. Okay. You can play, so this is a trajectory here, where now instead of staying through this driving here with the chaotic Lorentz system, instead of staying here at one potential well, you hop. Okay. So this looks like a stochastic system, and indeed you can use stochastic singular perturbation theory, or it's called homogenization of, to motivate here this equation, this SDE now, as an equivalent SDE for the long time behavior of this four-dimensional slow fast system. I say motivate because you do not know the exact invariant measure that's induced by this fast Lorentz system, but since it was proved by Warren Tucker that this one is mixing, the theory and all this works. Okay, so homogenization really works for this. We can though estimate this sigma. So this is a little digression now from data assimilation.
Sorry, what's epsilon?
Sorry, epsilon is a small parameter. So epsilon tells you how fast the time, it gives you the time scale difference between this fast process and this one. This evolves on an order of 1, and they go on this faster order, right? So we would like now to estimate this sigma here, and then what we would like to do is to compare data assimilation of this system here if we use ensemble filter, transform Kalman filter, if we use our VCKF, our variance constraining filter, and then if we say, okay, we replace the system by this system and now do data assimilation for this system. And we only observe this variable here, and we do not observe this variable here. Okay, so now we're gonna, that's our aim now. But in order to use this sort of reduced climate model, we need to know what sigma is. So sigma we can get from a trajectory of x by just coarse graining. So we create a long trajectory, and then we sample it. We need to coarse grain it to get something stochastic, because if we take the sampling time too small, the system is not stochastic then anymore. We would never be able to estimate a diffusion coefficient. Then, this is Q1, Q2. So this is for a two-dimensional system actually here. So then you coarse grain your state space, and then here, this is the blue is your true trajectory, and here are your sampling points. And now you measure how often do you go from here to here, and then that will give you estimates on your diffusion coefficient, the G. That would just be differences between, time differences between, I'm just going, it's like going to a Fokker-Planck equation and estimating the drift and diffusion coefficients. So when you do that, you can estimate the drift and the diffusion, and the differences here between those two pictures where I'm trying to measure the diffusion is I've used different delta t's, okay, for the sampling. So if my sampling is too small, so if my sampling is too large, then the drift term, if I estimate the square, is just the diffusion is just a drift term squared. So I can't see that, but there's a delta t, a sampling time, such that you actually measure roughly a constant diffusion. So this is phenomenologically that you can actually replace the system now, this system here, by one SDE, and we can measure our diffusion coefficient, and we still obtain the same drift. And now let's see how these three systems observe. So again, we measure the skill. So we only observe x, the slow variable. We do not observe for all experiments here. We do not observe the pseudo-observable. And this is logarithmically our delta t ops. Let's look at the green line first. The green line is the climate model. So we get horrendous skill here for small delta t, which makes sense because for small delta t, if it's really very, very small, stochastic model reduction doesn't work because it's a long-time result. So we wouldn't expect the climate model to behave very well here. However, it behaves, this is, I should say this is a preliminary result. So this is just because it's an informal talk, I present this here. We have to do many more experiments to really be sure what's happening. But we get quite a big skill improvement here for the climate model. Okay, so that's a nice result already, that this little homogenized equation can actually be useful for data assimilation. The blue line is the skill improvement if we use now our variance constraining filter. And this is probably some stochastic kind of, this should be, I mean, if we take more realizations on the average, maybe this will go to 1. These are things we have to look at. But we get, so there's no skill improvement here for small observation times. But there is one in this region here, and we expect for large observation times, we expect it to go back to 1, because then also the ETKF, the normal filter, in this large observation times, the ensemble will have acquired the correct climatic variance. But so in this, there's some intermediate range here where we get a skill improvement, and we looked at the different time scales. So the fast time scale here, okay, there you don't get any improvement. But the other time scale, the autocorrelation time, that's 200, so that would be past here. So if we go past the autocorrelation time, then we would expect, okay, that's enough now. If our observation window is larger, that we've actually lost all correlations, then we say, okay, we have acquired the climatic state, so our variance, we don't expect our variance constraining filter to work. I mean, it will work, but it will produce the same skill as the normal ensemble Kalman filter. But we also measured, well, finite size Lyapunov exponents. I mean, the fastest Lyapunov exponent for this 4-dimensional system is associated with a small Lorentz system, so that's too fast, the dynamics there. So if you look at finite size Lyapunov exponents, you get a time scale of 120, which is around here, and I believe it actually goes down here, so that's one border. And the other one is the exit time. Remember, this was this double potential, basically, so you can analytically calculate the time it takes to hop from one well to the other well, so all these transitions, the average time, and you can do that analytically. That's about 151. That's also around here. So you don't want to be too large than those two times, but you want to be the same order of this. So this is the time of these kind of mean exit times, or the finite size Lyapunov exponents, where we see a skill improvement of our system. And maybe that is interesting to do longer simulations. So what have we done? We've derived the variance constraining Kalman filter, and we applied it to a sparse observational grid. This was a Lorentz system, and we also applied it to a slow-fast system. And we've shown that the filter has better skill than ETKF for small in the observation times, and this would be roughly less than 6 hours if we use Lorentz's time scaling. And it has a better skill for both the observed and the pseudo-observables. It is stabilizing and can control filter divergences. However, there are filter divergences, and if we don't get good skill when in these blow-up situations. And we've also checked that the filter is robust to incomplete knowledge of your climatic state. So let's say we don't actually know exactly what the mean of our pseudo-observers and the error covariance. So we varied it, and we still got robust results in terms of the skill. And what we would like to do further as well, actually first do the slow-fast systems a bit more in detail and pin that one down, really what's happening. And we would like to investigate this blow-up further. So how can we control the blow-up? What's special about initial ensembles that produce blow-up and initial ensembles that do not produce blow-up? And so that's it. Thank you very much.
I was thinking more of a numeric weather prediction context. That way, you're running your system continuously, so you're never sort of starting from scratch. I was trying to, so in a sense, you have an ensemble method, it will just be always in its own climatological state. You're never going back. I'm trying to work out whether some of what you're saying is really the sort of initial startup issue, or whether you're thinking of a continuously running system, which is feeding observations in all the time and your extra constraints in all the time. So the ensemble should always be in essentially its climatological state. So what would your conclusions be in that context?
That's a good point. We have in this picture here, where we actually observe, and that's something strange that we don't quite understand it, but maybe maybe your comment here is helpful there. How we produced this figure here was we used, I think, 10 observation cycles.
So what did you start?
No, we start with the variance around the climatic. So we always start with a climatic, drawing an ensemble from the climatic error covariance.
So you're expecting the ensemble spread to reduce below that once you start assimilating observations.
Yes.
Have you reached the have you run enough cycles for that equilibration to occur? And typically, the observation density is fairly uniform in time on average. Obviously, fluctuates.
We've done spin-ups before as well. So we let the filter equilibrate.
So all that's happened.
Yes.
Before you start.
Yes.
Right.
But it may not be enough, and I'd like to talk to you about what you think is enough and how you measure this. I mean, we looked at convergences of PF, of our forecast variance and all this, so they all have converged. But we see something strange that I think it's a bug or something for this particular case here. I don't quite understand it, but this is with 20 or 10 or 20, can't remember, observation cycles. And you do the average of those. If you use 100, you use that skill, lose that skill. But we still made sure that we have a long spin-up time. So we thought about this, that there's a spin-up. And we get the same picture, so I don't quite understand this. This may not be. How would you measure spin-up? I mean, whether your spin-up was long enough?
Well, you look at the way the statistics evolve, I guess.
Yeah, we've done that. So it's usually for this system, usually after 2 cycles for the Lorentz system.
Well, obviously, I haven't worked so much with the Lorentz system with other systems, but I thought that doesn't sound very long to me. Maybe we should talk separately.
Yeah, no, but for this one we had, I think, even 100 cycles or so of spin-up. But that has to be investigated further.
So you pointed out the possibility for your RW to fail to be positive, definite.
Yes.
I don't have a sort of intuitive picture in my mind of what that means physically. Do you have any?
What it means physically is that your covariance actually is below the target. Okay. So that's the target or the climatic state, but you actually the eigenvalues of the SVDs of your forecast variance or your analysis are below that.
So if everything is actually, I was saying things are not strongly coupled in the Lorentz system, but supposing everything was quite strongly coupled, so you'll propagate information from the observations into the unobserved regions quite efficiently, then you would expect the system naturally to run with a much lower analysis error covariance matrix than your sort of climatological estimate. That would be the right answer.
Mm-hmm.
And, so you're not preventing that happening, presumably.
No, but we've seen that there will be some difference between, spatial difference between observation stations where you will lose that. Maybe it's not physically, but there will be one where you will lose information.
So, what's the sensitivity of this model problem to epsilon? So, if I increase the value or decrease when you don't have a clean separation in the time scale, so what kind of model, what kind of results you have?
We haven't checked that, so we try to be with small epsilons here, so that our climate model is a good representation of the true model. We particularly we haven't looked at, and I mean this is at early stages, we haven't looked at the dependence of this skill here as a function of epsilon. We haven't done that yet. But that's something to do. We definitely don't expect the skill of the climate model to behave that well for larger values of epsilon, just because it's a bad model for it. But what happens actually to how our filter will perform, we don't know. I mean, the linear problem suggests that the timescale separation is helpful, but it would be interesting, definitely, to look at how this thing behaves with epsilon. Yes. Okay, thank you.